Have you ever just stopped and looked around and wondered how all this stuff works? I mean, from a tiny drop of water forming a perfect little sphere to these giant skyscrapers that just reach for the sky, it's all engineering. It's these incredible hidden principles that shape our entire world. So today, we're going to pull back the curtain and take a look at the invisible forces that literally build our reality.
I mean, think about it for a second. How on earth can a million-pound plane just defy gravity? Or a massive ship made of solid steel float on water? It feels like it should be impossible, right? Like it's some kind of magic? Well, I promise you it's not. The answers are all right there in the science. And that's exactly what we're going to get into today.
All right, so here's our game plan. We're going to start with the hidden world of fluids, then get into the secret rules of flow. After that, we'll see how we're harnessing the power of fluids and building tomorrow's world with it. Then we'll switch gears to creating anything, making machines, and we'll wrap it all up by looking at engineering's next frontier. Sounds good? Let's dive in.
Okay, first up, the hidden world of fluids. This is all about unveiling the invisible forces that shape, well, pretty much everything. If we want to answer those big questions about planes and ships, this is where we absolutely have to start.
So the name for all of this is fluid mechanics. It's basically the physics of how fluids, so liquids and gases, behave, whether they're just sitting there or zipping around. And this isn't some dusty old textbook concept, okay? This is the core language that engineers use to design everything from the wings on a jet to the artificial hearts that save lives. It's that important. All right, so to really get a handle on fluid mechanics, you've got to know the rules of the game. These are the fundamental properties that tell us exactly how a fluid is going to act. First up, we've got density. All this means is how much stuff is packed into a given space. Pretty simple, right? A block of steel is way, way denser than the same size block of water. But that one simple fact changes everything. It's why ships float, it affects weather patterns. I mean, if you get the density wrong, your boat is going straight to the bottom. It's that critical. Okay, next is viscosity. The easiest way to think about this is how thick or syrupy a fluid is. It's all about its internal resistance to flowing. And for an engineer, this is a massive deal. You want jet fuel to have super low viscosity, so it flows easily. But the motor oil in that jet's engine, you need that to have a high viscosity to protect all the moving parts. It's a balancing act. And here's the perfect example. Honey, super high viscosity. It's thick, it's slow. Water, very low viscosity. It flows super easily. This one single property, how thick something is, determines everything from the size of our pipes to the power of our pumps. It's how we move the resources that run our world. And then there's pressure. This is just the force that a fluid pushes on a surface with. But here's the kicker. The deeper you go, the more intense that pressure gets. Just imagine the crushing force at the bottom of the ocean. That's why deep-sea subs have to be built like absolute tanks. They're literally fighting against the weight of the water above them. Okay, this brings us to a total aha moment in the history of science, Archimedes' principle. It sounds complicated, but the idea is actually beautiful and simple. An object in water gets pushed up by a force that's equal to the weight of the water it shoves out of the way. So, get this, if you can displace more weight in water than your own weight, you float. That's it. That's the secret. And boom, there it is. That's the answer to one of our big questions from the start. How does a giant steel ship float? Well, its massive hull is mostly empty space, so it pushes aside a huge amount of water, and the weight of that water creates a powerful upward force, buoyancy, that's stronger than the weight of the ship itself. It's not magic. It's just really, really smart engineering. Okay, so we've talked about fluids just sitting there, but now we're going to put them in motion. This is where things get really interesting. We're talking about everything from gentle streams to supersonic flight. Let's get into it. All right, don't let the equation on the screen scare you. This is Bernoulli's principle, and the core idea is actually a game changer. All it really says is this: when a fluid speeds up, its pressure goes down. That's it. Faster fluid, lower pressure. This one simple relationship is behind some of the most incredible technology we have. And the uses for this are just mind-blowing. Think about an airplane's wing. It's curved on top, right? That shape makes the air travel faster over the top than the bottom. And what do we just learn? Faster air means lower pressure. So you've got high pressure on the bottom and low pressure on top, and that difference creates lift. That is literally how a million-pound plane gets off the ground. It's the same idea that makes a rocket nozzle work and keeps a race cart glued to the road. Okay, let's zoom out a bit. We've seen the physics that makes a plane fly and a ship float.
Now let's see how those exact same principles are scaled up to build the world we live in.
Seriously, these engineering principles are everywhere. The roads we drive on, the dams that give us power, the sanitation systems that keep us healthy, even the barriers that protect our coasts from storms. It all comes back to controlling fluids and building strong structures. And if we just look at hydraulics, just the water side of things, it's huge. Urban hydraulics, that's what gets clean water to your house and takes the dirty water away. Agricultural hydraulics designs the irrigation that grows our food. River and maritime engineering stops floods. And hydroelectricity, that's clean power from dams. It's all just managing and controlling water, but on a truly massive scale.
All right, we've spent a lot of time on the invisible world of fluids. But what about the solid stuff? How do we actually make all the machines, the planes, the ships we've been talking about? Let's switch gears and look at how we shape the solid world around us.
So the traditional way to do this is called machining. You can think of it as subtractive manufacturing. The whole idea is that you start with a big block of metal or plastic, and you just carve away everything you don't want. It's exactly like a sculptor with a block of stone, just, with way more precision and powerful tools. And then there's the complete opposite of that, 3D printing. This is additive manufacturing. Instead of starting with a block and cutting stuff away, you start with nothing and build the object from the ground up, layer by tiny layer. It's a total game changer because it lets us create these incredibly complex shapes that you just couldn't make any other way. Just to give you a taste, here are a few key machining methods. There's what we call filling, or turning, where you spin a piece of metal on a lathe to make things like shafts and axles. Then you have milling, which uses a spinning tool to cut and shape complex parts, like gears. And of course, drilling, which is exactly what it sounds like. These basic processes, they're the building blocks of pretty much everything in our modern industrial world. Wow, okay, so we've gone from the physics of a water droplet all the way to building parts for a jet engine. It's been quite a journey. So where do we go from here? What's the next frontier?
Well, the future is actually a mix of old and new. Machining isn't going anywhere. You still need it for that super high precision work. But 3D printing is causing a huge revolution, especially in fields like medicine, with personalized implants, and in aerospace. And the glue holding it all together? Automation. AI and robotics are making our factories smarter, faster, and more efficient than we ever thought possible. So when you step back and look at it, from figuring out why a boat floats to literally building things layer by layer, engineering is all about solving problems. And as our tools get smarter and our understanding gets deeper, the only thing holding us back is our imagination. So I'll leave you with this. What's the next big problem we're going to solve? Thanks for tuning in.